steps. And now for landing, dead load for landing is 0.325, that is depth of waste slab, into 25, that is unit weight of RCC, into 1, that is width. As we know, for slab design we consider the width as 1 meter beam. Okay, that is equals to 8.125 kilonewton per meter, and live load is 1 into 5 kilonewton per meter square, that is equals to 5 kilonewton per meter width of landing. So total load is dead load plus live load, that is equals to 8.125 plus 5, that is equals to 13.125 kilonewton per meter. So factored load will be 1.5, that is load factor given in table number 18 of IS 456-2000, into that total load 13.125 kilonewton per meter, that is equals to 19.70 kilonewton per meter. So these are the loads. Now loading diagram of stairs shall be as follows. As I said earlier, in this waste slab of staircase there is uniformly varying load applied. Into landing portion the load is 19.7 kilonewton per meter, and in middle portion 24 kilonewton per meter. So now next step is design moment. So you can see here the span length, total effective span is 6.23 meter, the going portion is 3.3 meter at the middle, and both landing side is 1.465. Why 1.465? Because 1.35 is the length, is the span, landing length, plus half bearing, that is 0.23 by 2, that is equals to 1.465. okay, now design moment. So you can analyze here the reaction at support R suffix A is equals to R suffix B, that is equals to 2 into 19.7 into 1.465 bracket close plus 24 into 3.3 by 2. Okay, this is all right, that is equals to 68.5 kilonewton. Now maximum bending moment at mid span mu is equals to 68.5 into 6.23 by 2, that is total span by 2, minus within third bracket 19.7 into 1.465 into within first bracket 1.465 plus 3.3 by 2 bracket close, third bracket close, minus within bracket 24 into 3.3 by 2 into 3.3 by 4. okay, so mu is equals to 112 kilonewton meter. So this is the moment. So we have to resist that moment and design this staircase. So maximum bending moment allowed for a single reinforced section with Fe 415 bars, mu limit. Actually the formula of mu limit, you know, given I told this in every previous lecture. This the mu limit formula is given in annex G of IS 456-2000. So except FCK BD square, the other full portion, if we calculate for Fe 415 bars, that will be 0.138. So this is 0.138 FCK BD square. So 0.138 into FCK is 20 into 1000, that is B, into D square is 300 square into 1 by 10 to the power 6 to change the unit. Okay, so you can see here the value of mu limit is greater than the moment comes in the section. Hence this section can be designed as a single reinforced section. Okay, Now next step is area of reinforcement. So to find out the reinforcement, AST, area of reinforcement, we know we should use the formula from NSG of IS 456 2000. Mu is equals to 0.87 Fy AST into D within bracket 1 minus AST into Fy by BD to FCK. So mu is 112 into 10 to the power 6 equals to 0.87 into Fy is 450 into AST, that is unknown, into D, that is effective depth, is 300, we assumed already, within bracket 1 minus AST is unknown into Fy is 415 divided by B is 1000 into D is 300 and FCK is 20. So from this equation we can find out the value of AST, that is 1117 mm square. So if you use 16 mm dia bar, then the cross section of the bar will be pi by 4 into 16 square, that is equals to 201 mm square. Okay, so spacing will be 201 by 1117 into 1000, that is 179 mm. So we may provide 16 mm dia bar at the rate of 170 mm center to center, because we can deduct the spacing value, right? Now distribution steel is 0.12% of the area, because this is HYSD bar. So as per consideration of IS 456 2000 is 0.12% of the area. So 0.12 by 100 into 1000 into 325. So 325 is overall depth, that is equals to 390 mm square. So in distribution steel, if you provide 10 mm dia bar, then the spacing of 10 mm dia bar is equals to pi by 4 into 10 square by 390 into 1000, that is 201 mm. So we may write 200 mm also. So provide 10 mm dia bar at 200 mm center to center as distribution steel. So main reinforcement and distribution reinforcement is already we find out. Now check for development length. So the formula for development length you will find out from page number 43 of IS 456 2000. So LD is equals to 5 into 0.87 Fy by 4 tau BD, that is equals to 5 is dia, that is 16 into 0.87 into Fy is 415 by 4 into tau BD is 1.6 into 1.2, that is equals to 752 mm. Therefore, providing 800 mm length of bars at the points where LD is required as shown in figure. So let's check the final figure. So this is the figure as per design data. So as per design data, this is the figure of one flight, and another flight will also the same. So this is the cross-sectional view of the flight. Okay, you can check here the total length. Look, as distribution steel 10 dia bar is given provided at 200 mm center to center, and for main bars 16 mm dia bar at the rate of 170 mm center to center is given. Total overall depth is 350 mm, and the for development length 800 mm length is given, you can see here. Okay. So this is the ultimate drawing, and here the problem is end. I hope you enjoyed the class. Thank you for listening.